Alrighty, howdy folks. So in the last section we learned about graphs, trigonometric graphs. Especially we focused a lot on the sine graph, and then we said cosine looks almost like sine. It's just displaced, the sine graph displaced to the left by pi half, right? So we talked about something like that. And now let's look at the graphs of other functions, especially those of the tangent, cotangent, secant, and cosecant functions. I'm not going to spend a whole lot of time on secant and cosecant. I'll just point them out to you and talk about a little about them. Okay, most of my focus is going to be on tangent, and cotangent is going to be a lot similar to the tangent graph. Of course, obviously there are some differences. I'll point out to those differences, but if you understand how the tangent graph looks like, then you are in a good shape. Cool? All right, without much further ado. So this is how a tangent graph looks like. Of course, I mean, it keeps on going like that. The parent continues. That's what I mean by that. So let's focus on what we have here. And especially notice that a tangent graph, unlike a sine and a cosine, a tangent graph has actually asymptotes, vertical asymptotes. You remember those vertical asymptotes things from pre-cal 1? A vertical asymptote, 1 over x for instance, has a vertical asymptote at x equal to 0. 1 over x minus 1 has a vertical asymptote at x equals 1. Okay, and so on. So what in the world are these vertical asymptotes? A vertical asymptote is drawn at some x equals a when something happens. That something is the graph of the function would be approaching either positive infinity or negative infinity to the right or to the left of that x equals a. Okay, let me repeat that. We say a graph has a vertical asymptote at x equals a if to the left or to the right of that x equals a, the graph approaches either positive infinity, like it is in this case, or negative infinity. In this case, it just so happens that if we look at x equals pi half, there is a vertical asymptote, and to the left of pi half, we have the graph of tangent x approaching positive infinity, whereas to the right of pi half, the graph is approaching negative infinity. Regardless, even if one of these conditions had been satisfied, that is only to the left this is going to positive infinity, and to the right, well, right, it's a finite value. Even if that were to happen, we would say there is a vertical asymptote at x equals pi half. And this graph, it so happens that it has a vertical asymptote at not only x equals pi half, but also at negative pi half, negative 3 pi half, negative 5 pi half, positive 3 pi half, all kinds of integer multiples of pi half, right? Integer multiples of pi half, except 0, of course. 0 times pi half. With 0, you don't have, I spoke wrong. Okay, not integer multiples, odd integer multiples. How about that? 1 pi over 2, 3 pi over 2, 5 pi over 2, 1, 3, 5, 7. These are all odd numbers, right? Negative integers also, negative odd integers, negative 1, negative 3, negative 5, all for those pi halves, those multiples of pi half also, we have vertical asymptotes. That's the key. Then let's look at something else. Let me bring back that table of values of sines, cosines, and tangents. Now, at 0 degrees, which is same as 0 radian, tangent theta is tangent 0 is 0. Does the graph actually show that? Yep, at x equal to 0, tangent 0 is 0, and that's what the graph shows. And then at tangent pi sixths, so at when x equals pi sixths, somewhere over here, tangent is 1 over square root of 3 or square root of 3 over 3. What does that turn out to be? Well, square root of 3 is about 1.732. And so when I divide that by 3, square root of 3 over 3, 1.732 divided by 3 is about 0.57, something like that. Okay, so at x equals pi half, this has a value of 0.57. And at x equals pi fourths, tangent has a value of 1. So that means I have pi half here, so exactly midway is pi fourths. At that place, the y value should be 1, and it appears so, right? And at pi thirds, which is slightly closer to pi half, must have square root of 3, which is 1.732. Yeah, that's what it looks like. But at x equals pi half itself, tangent x is undefined. That's why we just see a vertical asymptote at x equals pi half, and there is no solid dot or anything like that. There is no specific value of tangent at pi half. Cool? That is the key to understanding this. And then what else? Another way of understanding this is actually looking at the graphs of sine x and cosine x. Okay, maybe I'll actually go to GeoGebra and show you all that stuff. Okay, where is GeoGebra? Yeah. Now, I can move this, which moves the x value. Okay, right now, if I let x fall on right on top of pretty close to 0, then what happens? I'm moving it. Come on. Okay, that's mighty close. So would you agree? The red graph is sine x, and the orange one is cosine x. So sine 0, x is 0 right now. Sine 0 is pretty close to 0. This is a round off error and all that. I cannot get it to be exactly on 0. That's why we are x happens to be 0.0002, and that's why sine x is pretty close to 0, but not exactly equal to 0. And okay, what's the point I'm trying to drive at? Okay, so tangent is nothing but sine x over cosine x, right? So when x is 0, we have 0 over 1, which is 0. Yeah, we saw that, we knew that part. And then when x equals pi fourths, notice, right? That's pretty close to 1, right? So these are the two, these two things seem to be fairly straightforward. However, the x equals pi half part, please absolutely pay attention to this part. The part I'm about to talk about is very closely related to something that you will learn in Calculus 1 called limits. Okay, so you really need to understand this concept really well. Okay, first things first. Would you agree that at x equals pi half, tangent x is undefined? Yep, that is because tangent pi half is sine pi half over cosine pi half. Cosine pi half is 0, so we have a 1 over 0, a division by 0 is undefined. At x equals pi half, guaranteed, there are no questions, tangent is undefined. So then the question becomes, okay, tell me what happens to slightly left of pi half. I promise you, I won't let x actually become pi half. I'll stay slightly to the left of pi half. Tell me what happens when I do that. Right? That is what is of essence. So you will learn that in calculus that this is called limit as x approaches pi half. Okay, so let us do that. Would you agree? I am letting x approach pi half as I move this x line, that vertical line, like this. Am I getting closer and closer to pi half? Am I letting x get closer and closer to pi half? Good. As I'm doing that, could you please look at the sine x over cosine x values? Where am I? I am to the left of pi half, but each time I am moving closer and closer to pi half. And I want you to look at what happens to the sine x over cosine x, which is tangent x. Okay, as I do that, 15, 16, 17, 18, 20, right? Oh, as we are letting x closer and closer to pi half from the left hand side, the sine value is positive and the cosine value is also positive, but cosine is approaching 0. That means we are dividing by a very, very small number. Pay attention to this concept, please. Why are these numbers increasing like this, 23, 24, 25, like that? That is because, let's say the top is just exactly equal to 1. 1 over some small number, 0.1. 1 over 0.1 is 10. 1 over 0.01 is 100. 1 over 0.001 is 1,000. You see, if the numerator being a finite number, if you divide by a number that is approaching 0, then that quotient will get larger and larger and larger. That is precisely what's happening. Let me come a little closer. Watch the denominator. The numerator is going to be pretty close to 1, so that's not an issue. The denominator is 0.0386. It's getting closer and closer to 0. So it is decreasing. And so the quotient became 25.8988. If I move a little closer, make it 0.0376, it's increasing. So this is the concept you need to understand. So I hope I have successfully demonstrated that as x approaches pi half from the left, tangent x approaches infinity, positive infinity. The numbers are getting bigger and bigger and bigger. So as what is called a limit, those numbers are approaching infinity. Cool? Okay, let's see how far I can go. 104, boy, 131, 278. Wow, 1687. In fact, if I had chosen a much smaller scale, I could have gone even closer to pi half without ever touching pi half. And then that number would have really gone even bigger. Okay, so this is the idea. So we can confidently say that as x approaches pi half from the left, tangent x approaches positive infinity. Let me repeat that. As x approaches pi half from the left, tangent x approaches positive infinity. Now let's examine what happens if we let x approach the same pi half, but this time from the right of it. Okay, so where am I? I'm farther to the right of pi half, and now getting closer and closer to pi half from the right. Okay, and as I do, notice negative 5.4, negative 5.49. But let's pause and ask, why are those values negative? Those values are negative because sine is still positive, 0.98 something. However, the cosine has become negative. So we have a positive number divided by a negative number. No wonder that's a negative number. So to the right of pi half, tangent x is certainly negative. And as we let x approach pi half from the right, get closer and closer, then it's going to become much larger and larger negative number. -7, -8, -9, negative, right? So this is the key. So this is approaching negative infinity because the numbers are getting larger on the negative side. So how far do we go apparently? If I get closer and closer, 14, 50, 70, 80. Wow. Oops. It did approach. It put a question mark. Man, this has got smarts built into it. So as I approached from the right, I could hit exactly by half and it went nuts. Hey, I don't know what that is, and put a question mark. But pretty close to -999, something like that. So for all practical purposes, we could take that as negative infinity. Cool. All right. Now I want you to tell me what happens. At x equals -pi12, guaranteed, this is going to be undefined at exactly x equals -pi12. But if we let x approach -pi12, once again, both from the left and from the right, can we figure out what happens? Notice, right now, would you agree that x is to the right of -pi12? In that case, what's happening to sine x? Sine x is still positive. Sorry, I take that back. Sine x is the red one. Sine x is actually negative, whereas cosine x is positive. To the right of, slightly to the right of -pi12. Sine is positive. Jeez, wake up, Sammy. Sine is negative and cosine is positive. I apologize. Right? So a negative divided by positive is negative. No wonder these values are negative. So if I let x approach -pi12, get closer and closer from the right, we still have the same situation. A negative number divided by a positive number, therefore it's going to be negative. But because the denominator is getting smaller and smaller, we are dividing by a smaller and smaller number. Therefore the quotient is going to be larger and larger on the negative side. Meaning tangent x as x approaches -pi12 from the right is going to be approaching negative infinity. Cool. Tangent x as x approaches -pi12 from the right or slightly to the right of -pi12, tangent x is negative infinity, whereas tangent x slightly to the left of -pi12, because both sine and cosine are going to be negative, their quotient is going to be positive, so would be approaching positive infinity. Whew. That is the point I'm trying to drive at. What happens to tangent graph at x equals pi12 and at x equals -pi12, both when x approaches pi12 and -pi12 from the left and from the right, so that we can figure out to the left is it positive infinity or negative infinity, things like that. Cool. All right, if you grasp that concept, I'm a very, very happy man. Where am I? What do I have here? Yeah, those are some of the concepts that I am trying to show you here. All right, so that's the graph of tangent. And then here I'm discussing at x equals pi12, pi12 minus. You read this as at x equals pi12 minus. What do I mean by pi12 minus? That is when x is slightly less than pi12, or when x is slightly less than pi12, or slightly to the left of pi12. Okay, slightly less than, which is the same as slightly left of pi12. What happens? So if we talk about a line segment or a ray, what do we mean? X equals pi12 is that vertical y-axis thing, but it's not quite fallen on top of the one. It is slightly to the left of it. I may have even exaggerated. This could have been shown to be much closer to the pi half line. Okay, in that case, we have positive divided by positive, but a small number, so that's a large one, and that's going to infinity. Pi half, to the left of pi half, tangent goes to infinity. To the right of pi half, which we denote as x equals pi half plus, then we notice that tangent graph is going to negative infinity, and we talked about that. Look at the number being a negative large number to the right of x equals pi half. What else? Yeah, at negative pi half, right? Negative pi half plus, meaning slightly to the right of negative pi half. This is going to negative infinity, and the negative number. To the left, positive infinity, because both sine and cosine are negative, and their quotient is going to be a positive quotient. So I discussed all of this. Cool. All right. Now let's look at linear transformations of the tangent graph. My hope is that we talked about this transformation thing with regards to sine quite a bit, that we can apply. We understood the main concept, so we can apply those concepts right away. What's that? Recall that if x old, y old is a point and y equals f of x, then the corresponding point x new, y u on y new on y equals a times f of bx plus c plus d is such that x new is x old minus c over b, y new is a old plus d, a times y old plus d. So based on that, could I ask you, hey, draw the graph of y equals 2 times tangent x? What does that do? Oh, a is 2, right? B is 1, C is 0, D is 0. What does A being equal to 2 do to this one? Since D is 0, 2 times y old is what y new is. X is not affected at all. So that means the whole tangent graph is stretched in the vertical direction by double the amount, meaning whatever the y value of a point is, that y value is going to get doubled. 0, when 0 gets doubled, at this point y value is 0, when that gets doubled, it still remains 0. That's why that point remains the same. Whereas if you look at this y value, which is 1, corresponding to this particular x, y value is 1. At that place, if you go vertically up, the red one should show 2, a value, y value of 2, and that's precisely what's happening. Where y value is 1 on the old one, its new value would be 2 times 1. Where the y value is 2, the old value is 2, then the new value is 4. Right? Everything is getting doubled. That's the point. All right. I have shown you just for one period how this transformation would be. And then, graph of tangent x is stretched in the y direction. Now, what about the graph of y equals tangent x plus 1? What would that mean? The old graph is y equals tangent x, but now apparently we have y equals tangent x plus 1. So let's interpret that in terms of a, b, c, and d. A is 1, b is 1, c is 0, d is 1 for this. Okay, so a is 1, so that means that x is not being affected. So a is 1, so y old plus d. So every y value has 1 added to it. Every old y value has 1 added to it. When you do that, this graph is actually scooted up by 1 unit. And that is precisely what you see. The green graph is y equals tangent x. If the y value is 0 here, what would the new y value be? 0 plus 1. Sure enough, the new y value at that x is equal to 1, right? If the y value is 1, say at this point on the old one, what would its value be? 2. 1 plus 1 is 2, and so on. So this is a graph of tangent x shifted up in the y direction by 1 unit. Cool. What else? y equals tangent of 2x. That's the graph where we have b is 2, c is 0, a is 1, d is 0. What? A is 1, d is 0. So y new would be just y old, whereas x new would be x old divided by 2. Oh, that means x new is x old divided by 2 means the tangent graph is squished in the x direction by twice. So if the x value here is something, then the corresponding x value for the same y value would be half of it. That's the whole idea. So this graph, the old graph, has been squished by an amount equal to twice the amount, or became half of the new value is half of the y value, half of the old value. Come on. All right. And the graph of tangent x is compressed in the x direction. Squished, compressed. All right, draw the graph of y equals tangent of x minus 1. Again, a is 1, d is 0, so y new would be y old. And b is 1, b is 1, c is negative 1. b is 1, so we are dividing by 1. But x old minus negative 1, that means x new is x old plus 1. X new is x old plus 1. Oh, that means the graph is scooted to the right by 1 unit. Exactly. In the x direction, as you can see, this is shifted by 1 unit. Same graph, same appearance of the graph. Even the asymptotes are shifted to the right by an amount equal to 1. What's the y value? What's the x value here? Pi half plus 1. That's the idea. Cool. Would you be able to do something like this? If that is the case, all I need to do is show you the cotangent x graph. It looks like this. Try to memorize how the graph looks like. So what it almost looks like tangent, but it is what leaning in the opposite direction, and the asymptotes, vertical asymptotes, are at 0, pi, 2 pi, 3 pi, 4 pi, and so on. Right? 0, pi, and then negative pi, negative 2 pi. Basically, these are integer multiples of pi. All right, so that's how the graph of cotangent x looks like. You need to know that. And once you do, you can apply the same transformations as before. And yeah. And to get the cosecant graph, we will be guided by the sine graph. So the orange one, as you can see, is the sine graph. And since cosecant is the reciprocal of that, since cosecant is the reciprocal of sine, this is the way the graph for cosecant looks like. Let's examine it a little and see whether or not it makes sense. At x equals pi half, sine x has a value of 1. Sine pi half is 1. Sine 90 degrees, right? So cosecant should be 1 over 1, which is 1. No wonder at x equals pi half, cosecant graph is at a y value of 1, right? Now, let's say over here, the y value of sine is actually 1/2, right? Half of this 1. Would you agree that cosecant therefore should be the reciprocal of 1/2, which is 2? So where this is 1/2, the y value is 1/2, there the cosecant has a value of 2. And as we get, again, as we talk about in terms of getting closer and closer to 0 from the right and from the left, as we let x get closer and closer to 0 from the right, that is x approaches 0 plus, then sine is approaching 0, positive 0, 0 from the right side, 0.1, it's becoming 0.1, 0.01, 0.001, so on. And 1 over that would be getting bigger and bigger and bigger, approaching infinity. No wonder we see an asymptote at x equal to 0 for the cosecant graph. And at the same x equals 0, if we let x approach 0 from the left, then we have sine x taking on negative values. Sine x is going to be negative 0.1, negative 0.001, negative 0.0001, like that. So each time we are dividing 1 by a number that is negative and approaching 0. So that's going to be approaching negative infinity, and sure enough, the graph points that out. Similar argument can be made about negative pi and pi. So have a sense of what the cosecant x graph looks like. And secant x, once you do that, draw a cosine graph and be guided by that as you draw the secant graph. Cool. That's pretty much what I can talk about in terms of these graphs, okay? That's it, folks.